Some of the laymen erroneously believe that the cosmic microwave background can never be used to study what happened at or before the Big Bang. However, with particle accelerators and unconventional apparatuses that uses quantum mechanics, we are getting closer to what happened at the Big Bang. What can cosmologists learn from the polarization of the cosmic microwave background? And how can we better understand the universe at least around 1 second after the Big Bang? Much of what scientists know about the universe's origins and early history come from a 50-year-old phenomenon called the cosmic microwave background, or CMB for short. This feeble radiation is the closest thing science has to a panoramic photograph of the contents of the universe as it was taking shape around 380,000 years after the Big Bang, when enough neutral atoms had formed to allow light to flow freely. Physicists at NIST's Quantum Devices Group created a novel form of CMB sensor array with very sensitive detecting components that can simultaneously monitor two spectral bands. Now, the CMB's strength is remarkably consistent, shifting just by 1 part in 100,000 from one location to the next. However, scientists may deduce information about density differences and energy distribution in the early cosmos from such microscopic variances. Scientists from across the globe have been mapping and studying this anisotropy for the past quarter century, and it continues to provide new discoveries. The polarization of CMB photons, on the other hand, was discovered much more recently. Other complementary parts of cosmic development are revealed by polarity variations. Density fluctuations, gravitational lensing, which is when light is warped by matter between us and the CMB surface, and maybe gravity waves generated at extremely early eras are all revealed by polarization shifts. Scientists are working on a new CMB detector from NIST that is not only more sensitive but also multichroic, meaning that it can monitor photon quality at 2 different frequencies in the same pixel at the same time. According to physicists at NIST's Quantum Devices Group, this technical advance boosts detection sensitivity while simultaneously offering a whole new second frequency range that may be used to identify the CMB from other astronomical sources. And they go on to explain that frequency coverage has recently emerged as a fundamental need of next-generation cosmic microwave background imagers, and that multichroic detectors meet this requirement without expanding the focus plane area, which is very costly. To detect and describe the polarization of CMB photons, researchers used quantum-based devices known as transition edge sensors. Each one is equipped with a small superconducting circuit that has been cooled to the edge of a critical temperature that distinguishes superconductivity from normal conductivity. According to NIST specialists, the new sensor arrays will widen the spectrum of information that can be collected from the cosmic microwave background. The entire mass of all cosmic neutrinos, which are continuously flowing across space, is included in one of these. Neutrinos are near massless particles that seldomly interact with matter. The cosmos was around 10 billion degrees Celsius 1 second after the Big Bang, and the sphere of space that will become the observable universe was approximately 10 light years in radius at that moment. During this period, neutrinos stopped interacting with baryonic matter and became separated from the primordial plasma, forming the cosmic neutrino background. According to the physicists at the NIST's Quantum Devices Group, neutrinos' mass has an influence on the structure formation and may be determined using CMB polarization. As an alternative, the cosmic microwave background could be used to determine neutrino mass.